In this slidecast, we'll cover implementing a binary tree class. Like a linked list, a node consists of a data part and links to the successor nodes. So we can store any kind of data in a tree node, and we make the data part an object of type item type. So we'll have a BT node class that corresponds to a node in a binary tree, and the data can be an item type. So we'll have a template class, and a binary tree node must have links or pointers to both its left and right subtrees. So these two fields, left and right, will be pointers to BT nodes. And this kind of structure is reminiscent of the nodes we had in lists. Here's a BT node class. It's a template class. It has a data field that's an item type. So this allows us to create binary trees where we can store ints or strings or any types related to the classes that we define. And then we have a left and right field value that are pointers to BT nodes. Here's a constructor that takes a data item and a left and right pointers to subtrees that default to null, or someone can call the constructor and give some non-null values. We have a destructor. Here's a toString method. And then we overload the oStreams insertion operator. And notice this is outside the BT node class. So our binary tree class will have, this will be a class that keeps track of a node, and it will have a root value that's a pointer to a BT node. So this helps us keep track of the root of the tree. And we can construct an empty binary tree or a binary tree with a given node as its root. And then we can also construct a binary tree with the given data at the root and the two given subtrees. So 3 different constructors. And here's a picture that illustrates a binary tree, an instance of the binary tree class that has a root pointer to this BT node. And this is the node that's the root of the tree that has the star character, and it has 2 subtrees, a left subtree and a right subtree. There's a plus and divide, and then here's some leaf nodes. So this is an expression tree where BT left points to the left subtree and the root node of the tree x plus y. So the left subtree here is an expression tree x plus y. And the right node points to an expression tree that's a divided by b. And the data field in the right subtree has the divide operator. Now here we have our header file. Notice here's a constructor that constructs a root that's an empty binary tree. And here's the other constructor we just talked about that takes a left and right child along with a data field. Here's the rest of our header file. Has some getters, our toString method. Here's a routine to read a binary tree from a stream. Here's a protected constructor to construct a binary tree with a given node as the root node. Here we overload the oStreams insertion and extraction operators. Now there are 3 constructors, the no parameter constructor and the constructor that creates a tree with a given node at the root. And this is protected because the client classes do not know about the BT node class. Now the constructor that builds a tree from a data value and 2 trees that will become the left and right subtree. Now if the left and right subtrees are of type binary tree char, and if the left subtree points to the root of the node of the binary tree x plus y, and the right subtree points to the root here of a binary tree that's a divided by b, then this statement here causes BT to contain the following tree. So if we have these two expression trees, this constructor will build this tree, where the root node is the multiply operator, and the left and right subtree are these earlier trees respectively, x plus y and a divided by b. The getLeft subtree function returns a binary tree whose root is the left subtree of the object on which the function is called. And it uses the protected constructor just discussed to construct a new binary tree object whose root references the left subtree of this tree. So here's our getLeft subtree. It's a template function. It's const, and if the root is null, then we get an invalid argument. We can't get the left subtree of an empty tree. Otherwise, it returns a new binary tree that calls the constructor with the root arrow left as the root of this binary tree. And there's a symmetric function getRight subtree. The isLeaf function is a Boolean function that checks to see if a node is a leaf, and it returns true if it is. And a leaf node has no subtrees. The toString method generates a string representing a pre-order traversal in which each local root is on a separate line, and if a subtree is empty, then the string null is displayed. So given this expression tree, if you call the toString function, it'll print the following list of values, sort of one node at a time. This is the pre-order. Let's see, this is the in order, I suppose. In the pre-order traversal, the pre-order will visit the root first and then the left and right subtrees. So we'll see the multiply operator, then the plus, then the x, and it tries the two subtrees which are both null. So these are the two null children of x. Then it will print y, which has two null children, and then it'll come to the right subtree from the root, print the divide operator, the leaf node A and its two null children, and finally the leaf node B and its two null children. Here's the C++ for the toString method. It's a template function. It's const. Declares an output stream. If isNull is true, then it'll just print out null. Otherwise, it prints the root and then calls getLeft subtree and getRight subtree, calls the toString method on each subtree. Now, if we use an input stream to read the individual lines created by the toString function, we can reconstruct the tree. If we read a line that represents information at the root, if it's null, we return an empty tree. Otherwise, we convert the input line to a data value and recursively read the left child and the right child. And then we return a tree consisting of the root and the two children. And here's a read binary tree method that takes an input stream as a parameter. And here's the implementation of what was just described on the previous line. Maybe stop the slidecast and study this for a few minutes. Now we can overload the extraction operator for a binary tree class to call the read binary tree function, and we can overload the insertion operator to call the toString function. And by doing this, we can read and write binary tree objects in the same fashion as we read and write other objects. So here's an implementation of overloading the insertion operator. And here's overloading the extraction operator. Now we do not provide copy constructors, assignment operators, or functioning destructors for the binary tree and the BT node classes. The purpose of these classes is to illustrate the binary tree abstract data type and not to provide a robust implementation. So this constructor, the three-parameter constructor, and the functions getLeft subtree and getRight subtree can result in multiple binary tree objects containing pointers either directly or indirectly to a given BT node. So one solution causes this constructor and these functions to make a copy of the subtree, and then the binary tree destructor can call the root's BT node destructor, which can then recursively call destructors for all the nodes in the tree. So there are many cases where this is inefficient, so we've decided to live with potential memory leaks for these classes. Now, an alternative is to use what's known as a smart pointer for the pointers in the BT node and the binary tree classes. And a smart pointer is a class that acts like a pointer, but it automatically deletes the object pointed to when the pointed to object has no owners. And the text describes smart pointers in more detail in Appendix A. And that brings us to the end of this slidecast.